Hello everyone and welcome to Unacademy classes. In today's class we will be discussing about casting. We will be doing revision. But first of all let me check if I am live or not. So it seems like I am live. So that is very good. So let's start the class and we will be doing a quick revision and along the way we will also be discussing about some questions. So overall after this class you will find that a lot of your casting is completed, because I don't think that we can complete it fully in one class, but in two classes surely we can do that. So just sit back, relax, and just listen to the things, listen to the discussion that I am just going to give. And also, if you are watching this live, then make sure that you are interacting whenever I am just asking a question, or whenever your doubt is just there to be cleared. So let's start the discussion. So once again, hello to everybody and welcome to Unacademy classes. My name is Abhishek Mishra and I am teaching manufacturing right here on this channel and also on the Unacademy's website, where you can just find me. I will share a link with you so that you can follow me there, and I will also share you a code. By using that code you can watch free classes in the Unacademy's website. And also, if you want to subscribe to get all the benefits, you can do that by just using the code and getting 10% off. So that code will be very will come in very handy, so just keep an eye on that. So I have secured All India rank of 662 in GATE 2020, that is this year's GATE examination, and I have completed my MTech from IIT BHU Varanasi in 2019, and I have got a good teaching experience of 2 years in mechanical engineering subjects. Some of my interests are photo editing, video editing, cricket, football, and I like all sorts of games. I will be taking this entire class in English, and also I will be discussing not only just the topic but also the important tips and tricks along the way, so that you can get a nice grasp of the topic, and also you can get the questions done with a very less amount of time. So we will be doing that. So just for that you need to attend this class in a relaxing manner again. And after this class I don't think that you have to give extra effort in the casting topic, because we will cover a lot. You just need to see this class whenever you want to revise, or you can just prepare notes during the class itself. Just write all the important things. Don't write the things that are just theoretical. Just listen to them and that will be it. You don't need to just go through them again and again. Just twice or thrice is fine. So first of all, just go to the Unacademy's website if you haven't already and follow me. And this is the link that you have to just paste in your browser, and there you will visit my Unacademy's profile, and there will be a follow button. Just click the follow button, and so you will be getting a notification whenever I go live, so you can attend the class there. So that is one thing that you need to be doing. And I will also be taking thermodynamics classes, so you should keep an eye on that by just looking at this profile. I will be sharing you more details about it in the coming days. So Unacademy app is free to download, and through this app you can watch all the free classes and all the classes after subscribing. So just give this app a go, download this app since this is free, so there is no harm. So just give it a go, and you can also follow me by using this app, and you will get notified by this app only. And therefore it is better to just look into this app for at least once, and if you are finding this app proper, then it is good. You are going to prepare in a better way, so that is always a great thing to do. And these are the things that you will be getting when you subscribe to Unacademy. So Unacademy subscription is giving you a lot of extra things which you are not getting by watching the classes on YouTube or by watching free classes. They are just to give you a taste of the Unacademy's main content, which is this daily live classes, which you will be just attending, and you can ask your doubts and answer polls all while the class is going on. Live test and quizzes are there to evaluate your performance, which is very important. By the way, you should start giving them as soon as possible. And by the way, just see Unacademy test series. They are giving you detailed analysis also, and that is very different than any other analysis or test series there in the online internet or anything. So just for that, you should subscribe to Unacademy. If you are not sure about long term, then you should subscribe to at least 1 month, and that money that you will be spending will be worth spent, because you will be investing you are investing your time by preparing for GATE examination, and that time is more valuable than the money. If you have the money, then you should totally provide that, so that you can prepare better, because ultimately at the end of the day you need your GATE score to be higher. And if you have resources, then just use that resources to achieve that high marks. And unacademy.com's subscription is definitely one of the best things that you can just get help from or just use to get that high marks. And structured courses are there, so all the in syllabus courses will be taught to you, which you can just see and cover in a proper way. And it will also be helpful for you to just go through this all syllabus without wasting time. So that's why the structured courses are very important, and they also creates a progressive study and a rhythm, which is also very must in GATE exam preparation. And unlimited access of content will be provided, so not only you will be getting live classes, you will be getting all the archived and recorded classes, and also you will be getting the test series. So a lot of content is there for you to just choose from. And here are the subscription prices for plus subscription type, which is basically classroom type subscription. And no cost EMI option is available for 6 months and above subscription plan, so that is also a nice thing to have. And you can select the 12 months, 18 months and 24 months plan to get the most savings, because they are providing you the most discount. And if you are not sure, as I have told you before, go with 1 month plan, and then just if you are just resonating with it, if you think that you need more months for preparation, you can always extend your membership. So 10% code, this code is very important. This code will not only give you 10% extra off, so your final prices will be like this is only possible if you apply this code, but this code will also provide you the free access to Unacademy classes. And you should totally go to Unacademy and check out their classes by just applying this code. Okay, so the free classes in the Unacademy's website will give you an idea that what this subscription service is like. So this code is giving you free classes and free notes also the PDF that I am just giving you right now, studying teaching you with right now, will be accessible to you when you visit my profile and download there by applying this code. So all the free contents are there for you to just take a look into, take a just assess by using this code. And also you can, if you want to subscribe, you can get 10% off. So this is a very handy code. Again, I am telling this because you can totally go to the website and be clueless what to do next. So this is the code that you should have when you visit the website or the app. And the other type of subscription is Iconic, which is for those who need more assistance, personal coaching, personalized test series. So that things are excuse me for that. So that thing, Iconic classes is for there. And again, ABHIMI is the code that you can use here also to get that, to get the 10% off. And this is the least possible price in which you can get an Iconic subscription for. Again, 10% off code is usable here and used here, then only this price is possible. And the prices I've shown, I think they are very reasonable, because the content, the teachers, number of teachers that are teaching the content, and also the what you can say, the test series and the unlimited access, the structured courses, so everything, the application also, that is also very top notch. The website is also top notch. So that all the things are very good for your online preparation, and you should totally check the Unacademy's website. By applying this code, you can just assess all the content there to get an idea. And join test series as soon as possible, because they are the ones that will properly give you an idea what you are, where you are standing, and what preparation you need more, where in which areas you are lacking. So that thing is a must. So let's just start our discussion now. So we are doing casting revision, and here are all the topics in manufacturing subject, and during our revision we will also go through important questions, but this is not the full complete class. This is just revision, so we will try to quickly discuss all the things. So in the questions also, I will not give you as usual a great amount of time to solve a question. I will just do a question and move on. And if you are watching this live, we can maybe discuss some of the points, some of the, I will maybe just give you some time to do that question, but still I will just do question in a few minute or a minute only, not a few minute, or under a minute I will try to do that, and we will just move on and discuss other topics, because again this class is also for recorded studying, and I need the students who are watching recording of this class to be quickly go through all the topics in the casting and revise them. So first of all, manufacturing processes. So manufacturing, what basically manufacturing is, in manufacturing we are giving the input raw material as input and converting that raw material as finished product, which is output. So input raw material, output finished product, and the process which is converting the raw material into finished product, that is converting the input to output, is manufacturing process. So basically manufacturing process converts raw material into a finished product. And the below image you can properly see that we have a gear blank, and we are taking it as an input and then converting it into a proper gear with teeth as an output, and the processes that are done in between converting them, are manufacturing processes. So it is a value addition process of the raw material to the raw material, sorry. So that is for manufacturing. Now let's move forward. So these are the classification of manufacturing: casting, forming, material removal, joining. So casting is a process in which molten liquid metal is allowed to solidify in a predefined mold cavity. So it should be very clear, we have a cavity where we have to pour liquid metal so that we can obtain our final product after the liquid metal has solidified. Forming. So forming is a process where we are changing the shape of a metal piece by plastic deformation process to get the required object or required product. Material removal, the name itself is saying that we have to remove material. You have to do the subtraction of material to get our desired product or desired geometry, and it is also known as machining process. Joining, again the name itself is clear: welding, brazing, soldering, adhesive bonding of materials. So this all processes are joining, means we are going to join in them or make a joint of joining of metal pieces or some work pieces. So we are doing it differently, and these are the processes that I have just mentioned. So these are classification of manufacturing processes which are very important for your GATE examination, and which are there to be studied for your GATE examination. So let's go through the first manufacturing process: casting. So casting, as I have discussed, it is a manufacturing process in which molten metal is allowed to solidify in a predefined mold cavity. Steps in casting are pattern making, core making, making mold cavity, melting and pouring, and finishing. So this is the order also. We are first making a pattern, then core, and by the way, core is used to make hollow structures, and then we are making mold cavity, and we are making mold cavity by putting the pattern in the mold box and then just packing sand around it and then drawing out the pattern, and then the impression or the cavity that is left is just the liquid metal is poured into it to get the final product. And after all this, we are doing finishing to remove the undesired parts or the secondary cavities. So what secondary and primary cavities are, let's see here. So here the primary cavity is this. So let me just show you here. So this is your primary cavity, means the final product will be in the shape of primary cavity. So as you can see, when you are pouring the liquid metal, so from here, let's say you are pouring the liquid metal. So what will happen when you are pouring the liquid metal, you are filling this entire cavity, this, this and this with the liquid metal. So you will stop only when all the things are filled. So after you are pouring of liquid metal and the liquid metal has completely filled, it will solidify due to temperature difference between the liquid metal and the molding sand. And during its solidification, the whole cavity where liquid metal is there will be solidified, and after the solidification it will be like this. So as you can see, we have our primary cavity and non-primary cavity, which is the gating system with the shaded figures. So the shaded figures are the gating system which we don't require in our final product, so we have to finish them out, cut them out. So this is our final product, which is only in the shape of primary cavity, and the rest of the secondary cavity, that is pouring basin, sprue, runner and riser, are there to just create passage and just create this whole casting process possible. So again, remember this terms, primary and secondary cavities, and what we have to do and why they are being used. So that will be it. And again, I am just going to quickly discuss here, give you an overview of what pouring basin, sprue, runner and riser are. So pouring basin, you are first pouring the liquid metal inside this pouring basin. It is the first thing that the liquid metal is encountering in our gating system, and that pouring basin will make sure that the liquid metal is smoothly going into the sprue, which is a vertical passage, and that sprue will just pass the liquid metal to runner, which is horizontal passage, and that runner will lead the liquid metal to the primary cavity, and the section passing which the liquid metal enters the primary cavity is gate or in gate, and it is this section. So here you will have your gate or in gate, which is the final section after which liquid metal enters the primary cavity, and your riser is there to compensate the shrinkages, because when the liquid metal will just solidify, it will shrink due to alpha, that is thermal expansion coefficient or contraction coefficient, and you need some extra metal so that you can compensate the shrinkages, and that extra metal is in riser, which will provide the primary cavity that extra metal when it is shrinked or contracted. So that is the job of riser. Another function of riser is to allow the gases to escape, that is forming or generating during the casting process. So riser are doing these two things, and we will talk about riser more when we just move forward. So let's do that. So this is mold box. In the mold box you have two parts, scope and drag. So scope is the top part, drag is the bottom part, and we can also have a middle part, cheek, and these parts are just the intersection of these parts are parting line. So that you have to also remember that scope, drag, and the line which is intersecting them is parting line. And here you can see that scope and drag, how they are used or how they look like in the real life example. And you can also see the cavities and core also. So here you can see core also. So this is nothing but core, which is used to create hollow structures. And by using this cavity and this mold box, scope and drag, you are creating this product. So this product right here is two castings from the sand mold, as you can see, and first one is bronze and second one is aluminium. And just look into the final casting and just look into that these are having the internal holes or internal hollow structures, because cores are used, so they will obviously have them. So but just for your understanding, just look into that this the holes are there in the exact places where cores are placed. So again, we have cope and drag here, which are the top and bottom part respectively, and the line which is dividing them is parting line. So this is about mold box. Now we will go through a casting example very quickly. So pattern is set in drag with gating system. So here you can see a pattern and a drag box, and the pattern is set into that drag box along with gating system. Next we are just putting the sand around it and hand packing it to make the cavity, and after that we are doing ramming. So ramming is done to obtain the dimensional stability of this whole mold, and we are striking off the excess sand after that, because that excess sand will lead to not closing of your cope and drag box properly. So that needs to be just strike off by striking rod. And here is the drag ready for the cope. So drag is ready, bottom part of the mold box is ready. Inside the mold box again we are creating cavity, just for your information there. And now we are doing the same thing with cope, having this gating system, that is a sprue you can see, a riser you can see, and also the pattern ready. And then we are just doing the packing of sand and then ramming it with a hand rammer. And then we are doing venting so that the gases are allowed to escape properly, so that we have proper permeability, and porous structure is not formed, because porous structure will lead to weak casting. So that we have to just take care here. Then we are drawing out the pattern so that cavity is left, and here you can see pattern is completely drawn out and we are left with a cavity. And now we are setting up a core, because our final product, as you will see, it will be having a hollow inside structure. So that is only possible due to this core. So this core is in the shape of this core, you will get the hollow structure also in the size of this core. And this is the cope and drag finally ready to just close, and then we are clamping them so that they are properly held. And then we are pouring the liquid metal, and finally we are getting this final finished product, which is pump housing casting. And this is done by removing the gating system and all that. This is finished product, finished casting. And you can see the hollow structure here also, which is only possible by the use of core. So that is the whole casting process, and I think you should now properly understand the process from the start to end. And you can also give answers if it is asked what are the step of processes and how, in which order they are done. So you can also give them that, give the answer of that. And now let's see the examples: door handles, locks, the casing, housing for motor, pumps, wheels of many car, gas turbine blade, which casting process, investment casting, gold ornaments, dentures, that is false teeth, hollow cylindrical pipes, pulleys, etc. Casting is also heavily used in toy industry to make parts, example toy cars, plane, etc. So I will give you one more example here, which is there for casting: machine beds. So machine beds are also manufactured using casting process, more specifically sand casting. And as you can see, machine bed is very heavy, it is obviously 1,000 kilograms heavy, and door handles are few grams heavy. So casting is a very versatile process. In this you are not only creating small parts, you are also creating a large heavy parts. So this is one of the advantages of casting. And speaking of advantages, now let's discuss that. So advantages of casting are complex shape parts with internal cavities can be easily produced. So you can easily do that, because you have to just create the complex shapes and then pour the liquid metal. So that is done easily in casting. And it can be used to create small to very large size objects. As I have told you before, engine blocks is also a large size object that we are making from casting process. Economical with very little wastage. And why it is economical with very little wastage? Because the extra metal which is there in the secondary cavity or the gating system can be just remelted and reused. So we have very little wastage, and therefore it will become an economical process. And casting metal that is obtained from casting is isotropic, that is in the same direction or along the same direction, we will obtain same physical and mechanical properties. But remember, along any direction, not all the direction, because it is isotropic. Possible to cast practically any material, ferrous or non-ferrous. It is totally possible to cast both of the material by using the process. Now here it is very important, the bottom figure, and we will talk about it, but after we have discussed the limitation, we will also discuss this very quickly. So casting don't have a smooth surface finish. You have to remember this. Surface finish is not good for casting processes as compared to the other process. It is a laborious process and time consuming process. So that is expected because there are a lot of steps involved and you have to do all the step neatly and properly. So it will take some time and also take some effort. Possibility of gas defects is there. Again, molten metal, when you are pouring, the gases will be generated due to that temperature difference, and also due to air aspiration effect, things like that, if your casting system is not properly made. And we will talk about the air aspiration effect as we move forward. Casting objects don't have uniform mechanical properties due to non-uniform cooling. So the cooling will be non-uniform due to the surface area which is in contact with the liquid metal is different for different reasons, and that will change the rate of cooling, and therefore we will have a non-uniform cooling, and therefore we will have a non-uniform mechanical properties. The best mechanical properties or machining properties are at the center, so better machining properties towards the center. So there you can find the uh, machining to be done very easily, and that is why there, and that is due to the coarse and equiax grains there. So and in the center you can see coarse and equiax grains, which is just making the center region having better machining properties. And as we move towards wall, we will find first that columnar grains or dendritic grains are there, and near the wall we will find fine and equiax grains, which is also called chill layer. So coarse grains center, coarse grains means big soft grains, so therefore ductility of coarse grains is higher than fine grains. Equiax means stress free grains, again that will make the better machining properties by increasing the ductility of that grains. And columnar grains are not going to have that much of ductility as compared to coarse, because they are not equiax, there will be some stresses there, and they are also not that much ductile, therefore not better machining properties than coarse grains, which is at the center. And near the wall there is chill layer, so you can get asked in your gate examination that what is a chill layer, or where or in the chill layer what type of grains you find. So in the chill layer you find fine and equiax grains, because that layer is near the mold wall, so their solidification rate will be very high, because the mold wall is having a less temperature than the molten metal temperature, so solidification will start there first, and therefore this fine and equiax grains are visible there. And this microstructure of casting is very important. A gate question has been asked already, and I just want you to just properly just draw this figure, or if you are not drawing this figure, at least just look into this figure and note down some of the things like near the mold wall, fine and equiax grains, chill layer, and then we are just do the arrow, create an arrow and draw them one by one, and the arrow should be wall towards center. So you can without drawing you can get the idea here. And here was the question, GATE 2018 1 mark set 2. It was asked that during solidification process of molten metal, grains near casting uh, or grains in the casting near mold wall are. So by looking at the figure you can say that they are fine and randomly oriented. And why? Because they are near the mold wall, so their solidification rate will be high, and they will be solidification rate will be towards from the center towards the walls. So they will be going, heat transfer will be occurring away from the center towards the wall, so therefore fine and randomly oriented grains are obtained near the wall. So that will be it for this question. Now let's quickly move to the next thing. So the next here is the pouring temperature. So you are pouring liquid metal into the cavity, and that liquid metal is then solidifying. So that liquid metal, first of all, needs to be, a metal needs to be made molten or liquid, and therefore we have to make sure that it is melting point temperature, at least that much temperature is there, because then only it will be in the liquid form. But we are giving some extra temperature, which is called as degree of superheat, 100 to 250 degree. We are providing this so that the molten metal completely fills the cavity and not solidify soon. So the molten metal will solidify as it comes to contact with the mold wall. Because of the temperature difference, heat transfer will be there, so it is quite easy to understand. And we don't want it to solidify without filling the whole cavity fully, therefore we are giving this degree of superheat, which is 100 to 250 degree. Now we have to move forward, because this is it for this uh, pouring temperature discussion. Now we will discuss, have a very lengthy discussion. I think 20 to 30 minutes can be taken in this discussion. We will discuss about pattern, and in pattern what we are going to do, we are going to learn about different pattern materials, different allowances, what pattern is, what are some important questions. So all this will be cleared in the matter of some minutes, so just stick with me. So let me just check one thing out. So let's start our continue our discussion here. So we were now talking about the casting pouring temperature. Now we will move our discussion to this pattern. So let's quickly go through all the things that we need to cover here. So first of all, what pattern is? Pattern is, uh, I was just checking out if the class was live or not, or if there are any student watching this class live, so I can answer them. So let's quickly move to the discussion. So pattern is a replica of the final casting to be produced with some allowances. So these allowances, these modifications are there in the screen. But again, what pattern is used for? It is used to create cavity. But pattern and the part to be made, that is pattern and the final casting. For example, if you are creating a doorknob, then the pattern which is used to create the cavity, and then in that cavity molten metal is poured, and a doorknob is produced. So that doorknob, which is the final product, and the pattern of that doorknob shape is not exactly same, because pattern is having some allowances, some modifications. And why we are going to do this modifications, provide this allowances, we will discuss it right here. But what these allowances are, let's quickly go through them one by one. Shrinkage or contraction allowances, name should be clear. Name should be just making it clear that why we are providing it. Draft or taper allowances, matching or finishing allowance, shake or wrapping allowance, distortion or camber allowance. So these are the allowances that we need to study for gate examination. Shrinkage allowance. So we have this first allowance, which is shrinkage allowance. So if your liquid metal is solidifying and it has just converted into solid after the phase transformation or phase change, then when it has reached the solid form, it will still be at higher temperature than the room temperature, and it will then lose its temperature till it reaches thermal equilibrium there, or till its temperature becomes equal to the ambient temperature or room temperature. So that solid shrinkage, which is the shrinkage which will happen when your casting or your liquid metal is made into a solid form, is compensated by providing shrinkage allowance, and shrinkage allowance is provided to pattern. And see here, very important thing, that we have three types of shrinkages: liquid, solidification, and solid. So the first two type of shrinkages are compensated by the riser, but the last shrinkage is compensated by providing some modification or giving some allowances to the pattern, and that allowance is called shrinkage allowance. So this graph is also showing quite clearly what are the shrinkages, and where they are happening, and what are the temperatures involved. So pouring temperature is the maximum temperature, and in this temperature you are just pouring the liquid metal. Then you are going to get to freezing temperature, where phase change will happen, and then ambient temperature will be the final temperature, after which your process will be completed and thermal equilibrium will be reached. So between this C and D, the shrinkage will happen. In every process A, B, B, C, C, D, we can expect some shrinkages, but between C and D, the shrinkage that is happening is compensated by shrinkage allowance, and from A to C, the shrinkage that is happening is compensated by riser. And for solid shrinkages, the temperatures TF and TA are the ones who are going to play a role. And let's see what are the notes written here. Solid shrinkage allowance is also called as pattern making allowance. So that is also a thing that you can remember, because if pattern making allowance is given, then you can just quickly know that it is talking nothing but solid shrinkage allowance. Shrinkage, solid shrinkages are expressed in mm per meter length. So it is expressed for each side. For example, if you have this three sides, length into breadth into height, then you will have solid shrinkage given for example, if you have solid shrinkage given like 1 mm per meter, so it will be 1 mm per meter for this every sides, or it can be also given as 3%. So you can be just get this idea that, or you should know that this is for every side. So for length, it is increasing the length by 3%, it should be increasing breadth by 3%, height by 3% to compensate for the shrinkages there. So for a side, we are providing solid shrinkage. But liquid and solidification shrinkage, that is the shrinkages that are happening in AB and BC, are expressed in percentage of shrinkage volume. That means they are not given for a side, they are given for whole volume. So if you are given that 5% of a liquid shrinkage is happening, you should know that 5% is percentage of the volume. So that thing is also written in the slide, which you can take into just account. And the solid shrinkage allowance depends upon the coefficient of thermal expansion alpha, and for a dimension L, the shrinkage allowance is here. So again, this is just a basic thing. The shrinkage allowance is depending upon alpha, that is coefficient of thermal expansion, L, that is dimension, and TF and TA, that are the temperatures in which the solid form is changing its temperature. So that are the things in which a solid shrinkage allowance is depending upon, and you should know these things. And again, I am making this revision very quickly, so the things here that I am just providing you, the information here, are the ones which are important, so don't miss any of them, just learn them. And I am definitely sure that you are going to get benefit when you are giving an exam. Riser is designed to, so I have told you very important concept before, that a riser is designed to do the liquid and solidification shrinkage compensation, and therefore the riser is placed above the casting and it should be freezing after the casting, because if it freezes before the casting, then how it can compensate for the shrinkage, how it can provide the liquid metal there. So it needs to be just freeze after casting to just compensate for this shrinkages that is happening in the region A to C, that is liquid and solidification. So it will be B. So sorry, it will not be B, it will be A, because as I have discussed before, it should freeze after the casting freezes. The contraction allowance provided on the pattern and core boxes compensate for which type of contraction? Contraction is basically shrinkage. So pattern, if shrinkage allowance is provided on pattern and it is there to uh, compensate solid shrinkage, the rest of the two are compensated by riser. When there is no room temperature change, the total shrinkage allowance on a pattern is independent on. So the shrinkage, solid shrinkage, which is what this shrinkage allowance is compensating. So this solid shrinkage is given as alpha L freezing temperature minus ambient temperature. So let's see what are the things this shrinkage allowance is depending upon. Pouring temperature, no, it is not anywhere to be seen, so it is independent of pouring temperature. You can just tick that, but we will make this habit of going through each and every option to make less mistake, because some other option can be there which is providing even better answer. So let's make this a habit. uh, Freezing temperature of the liquid metal, so yes, it is depending upon TF. The component size, yes, L. Coefficient of thermal expansion, yes, alpha. And it is said that there is no room temperature change, so it is also depending upon TA, but since there is no room temperature change, so it will be independent of that here, but it is depending here when there is change. So pouring temperature is nowhere to be seen here, because the metal is already made into solid, then it is having this temperature change and shrinkage after that or during that temperature change, and that allowance is compensating that. So pouring temperature is not the factor that we have to take into account here. When cooling a cubical casting of 40 mm size, it undergoes 3%, 4%, and 5% volume shrinkage during the liquid phase transition and solid state. The volume of the metal compensated from the riser is. So these are the percentages of shrinkage in the liquid, solid, and the phase change state, and we have to find the volume of the liquid metal, or the percentage of volume of liquid metal which is to be compensated, or whose shrinkage is to be compensated by the riser. So liquid and solidification or phase change, that is the things that are to be compensated by the riser. So these are the first 2 points or the first two values. So it will, their sum will be 7%. That is the answer here. Gray cast iron blocks of size 100, 50, and 10 with a central spherical cavity of diameter 4 mm are sand cast. So what it is given that we have a cast iron block and we have a spherical cavity. So let's make a cavity here, or let's make it like this. And we are provided with the sizes here. And we are also provided that there is shrinkage allowance given to pattern, that is 3%. So ratio of volume of pattern to volume of casting. So this is to be found. And shrinkage allowance, what it is doing, it is making this pattern size larger to compensate for the shrinkage or contraction. So by just looking at this ratio, you can tell that this value will be greater than 1. No questions asked. Why? Because volume of pattern is greater because it is given some allowances which is making its size larger, therefore its volume will be greater than the volume of casting. Now there are two ways to do this question. One is a hard way, which is obviously going to involve some of errors due to the long calculation there, and other is the smart way. So I'm providing you this very important tip and trick which you can just use here also or in questions like that. So this is the volume of casting. So you can take that volume as V, and that volume is the volume of this whole block minus the volume of the spherical cavity. So that will be the volume of casting. But that volume is given some allowances, and that shrinkage allowance, as I have discussed before, they are given to the sides. So this 100 mm side will become 103 by 3% increase, it will become 51.5, it will become 10.3 mm. So this is due to this 3% allowance. And how you are getting 103 from this 100? You are multiplying 1.03. You are here also multiplying 1.03, because that is the factor that you have to multiply to get this 3% increase. So in anything, if you need to get 3% increase, you are needing to multiply 1.03 to increase it by 3%. So what we will do is we will take volume of casting simply as V and volume of pattern as V, but now we have to multiply this 1.033 times because there are 3 dimensions here. So it will be 1.03 cube, and you have to just simply cancel it out and simply do the cube here to get the final answer. No need to calculate the whole volume and then calculate the pattern volume and then divide them. Just take the common factor out and cancel the volume, and then you will be getting the answer in a matter of few seconds without any chance of making mistakes after doing the long calculations. So it will come out as 1.09, which is the right answer. So this is very important tip. What we have done, we have just taken out the factor which is there, which was increasing the size of the pattern from the casting, and then we just cancelled out the common factor, that is volume, and we obtained our final answer. So we will discuss more tips like that in our coming questions. So let's move on to the next question here. And again, the volume is coming out greater than 1, which is expected because volume of pattern is greater than volume of casting because we are making the pattern larger. So that is one thing that you can always remember to check the answer by just your concept. And here are some things that you should be aware of in the solid shrinkage, that for brass, 4 materials you have to be aware of. So let's discuss that 4 materials. The first material is brass. The second one is aluminium. Then we have steel. Then we have gray cast iron. So for solid shrinkage, these are the 4 materials that you need to be aware of, or you need to just remember. And what these materials are, why you have to learn about this material, because brass is having maximum solid shrinkage, so therefore it will shrink maximum after becoming solid. So you need maximum uh, allowances here given to the pattern when you are using brass. So largest size of pattern due to this shrinkage allowance providing is brass material. Aluminium requires more volume of riser because it is having liquid and solidification shrinkage maximum, and total shrinkage both solid and liquid and solidification shrinkage, all three of them are maximum. All three of their sum is maximum for steel, so we have to provide steel adequate riser volume also, and adequate size also to compensate this shrinkages, so that we get our final product as desired. And gray cast iron is a little bit of different than other materials. Why? Because in the liquid and solidification state, that is in the states which is there before it has become a solid, that is liquid and phase change, it is expanding when the temperature is decreasing, and this is happening due to conversion of carbon into graphite flakes. Gray cast iron will have carbon because it is a steel, and therefore it will definitely have some carbon, and that carbon is converting into graphite flakes, and due to that expansion is occurring instead of contraction that we are seeing in the other materials. So this is some odd one. So you have to remember this gray cast iron also. It can be asked what is the reason or of this expansion during this temperature change, or during this liquid and solidification uh, shrinkages, or not shrinkages, it is not shrinkage, it is expanding. So you will just simply say carbon converting into graphite flakes, that is the reason. That will be enough for gate. And in the solid state it is simply contracting like rest of the other materials that we have studied. So overall you have to remember brass solid shrinkage maximum, liquid and solidification shrinkage maximum aluminium, steel total shrinkage maximum, gray cast iron expansion in the first two phenomena liquid and solidification. So that is due to the conversion of graphite flakes from the carbon. So that will be it for this discussion. Now let's see what we have. We have a question here: which of the following material requires the largest shrinkage allowance while making a pattern? So largest shrinkage allowance is given to the one who is having maximum solid shrinkage, and that is none other than brass. We have studied it here. You can also just look into that here also, the first line. So again, these four materials, just write their name and what they are, generally why we are studying them and why we should be aware of them. No need to just remember this 6.5 percentage. It is just to give you an idea about the shrinkage. So that idea need to be just look into and move on. No need to just remember this. So remember only the material and why they are being studied here. Shrinkage allowance on pattern is provided to compensate for shrinkage when. So shrinkage allowance is provided on pattern, and we are providing this to compensate for shrinkage when temperature of solid phase drops from freezing to room temperature. So that is option C. I will not just take more time because we have studied this very properly. So here you can see C and D, between this the shrinkage that is happening, and that temperatures involved are TF and TA. So due to this shrinkage we have to provide a allowance, which is shrinkage allowance, which is provided on the pattern to compensate this solid shrinkage CD, between CD. And yes, let's move forward. So we have this question in which a cubic casting of 50 mm size is provided. So its volume, its size is 50 mm, its volume will be 50 cube, since cubic. And there are two types of shrinkages happening: solidification and solid, and both are volumetric. So in this question liquid shrinkage is not given, so we will just ignore them. It is not given, so none of our concern. And here the solid shrinkage or solid contraction is given as volumetric, so just remember that. So no riser is used, So you will find that your shrinkages that are happening will make the size smaller. There is nothing in the riser, or there is no riser to compensate them and to make the size not get small. So the size will get smaller, and we have to assume uniform cooling in all directions, so that is just an assumption. We have to find side of the cube after this two contractions. So what we will do is we will draw this figure. Simply draw this graph because it will be making your whole process more error free, and more quickly you will just do this in a more neat manner. So always remember that if you are getting this chance of drawing a figure, just go with it, just draw a figure. So this liquid A and B, where the casting or the molten metal is liquid, till B there will be no contraction because it is given in the question. The contraction is only occurring in solidification and solids. So we will have at A 50 cube volume, and at B the volume will still be 50 cube, but here at C the volume will be 50 cube into 0.96 because of the contraction of 4% there. And this will become even less when we multiply this smaller volume with this 0.94, because 6% of contraction is occurring when the material is converted into solid, and then it is having its temperature change. So solid shrinkage is 6%, and that is volumetric. So this will give us the final volume of the casting that is obtained after the shrinkages. So it will be 50 cube into 0.96 into 0.94. So that will be 112,800, and it will be in cube units. And when we, this is A cube, AF cube, A final cube. So to get A final, that is final size of the casting, we will have to just take the cube root here. It will be 48.317. So let's take it 32, and this will be in mm. I think the units were given in mm. So yes, mm. So 48.32 is the answer. So that is the final size of the casting, and how easily we can obtain this, and how look into this figure and just see. If you have drawn this figure, then there is very less option, less possibility of making error. So always draw this figure. It will take just 20 to 30 seconds to do that, but your chance of making the question correctly, doing less error, goes increases immensely. So that is obviously is the main thing that you should be looking into, because you don't want silly mistakes to occur, and by drawing the figure you can eliminate them by a larger extent. Gray caster and block size is given. Pattern is having an allowance of 1%. So that pattern making allowance is given. So this is solid shrinkage allowance. As I have told you before, it can be also appear in this name. And we have to find the volume of pattern to volume of casting. So this ratio will be greater than 1, because volume of pattern is greater, because it is provided with this allowances, as I have discussed before. So you will just cancel this or just look into this option and tell them that this is wrong by just looking into it. And this pattern making allowances will increase this 200, 100 and 20 by 1%. So 1% increase will be there in each and every side that is shown here. And to do this 1% increase, we will multiply 1.01 to this dimensions to get the final size. So there is two options that you can do this question in. So volume of pattern divided by, so my process is (1.01). There are three sides which will be increased by this 1%. So cube volume divided by volume. So this volume totally will increase, but this will be our final answer, and it will completely, you can say by just looking, that it will come greater than 1.01 because we are making it cube. So the answer will be D. No need to do calculation, but after doing calculation you can also find it as 1.03, which will be the ratio of volume of pattern to volume of casting. So there is one more option where you can increase this 200 by 1 percentage, it will become 202. Then you have to multiply this will become 101, this will become 20.2. Then you will have to find the volume of casting, which is simply multiplication of all the dimensions provided of the casting. So if you do this also, you will find the same answer. So my formula is better, my trick is better, because it will do the question quickly, and there is less calculation, so less possibility of error. So that is the answer here, and I should just quickly select the answer here. It should be D. So let's move forward. And this question, see how much easier this question is, and this is only 2 marks question. So just look into the uh, process that we followed. In one line we obtained the answer. Here look into this, here we have obtained the answer in one line only, and this question is of 2 marks. So again, you need to just be aware that gate questions are not that hard. They need to be just understood properly, and there are some tricks, some tricky things that is provided in the question, which you have to just decode. And if your concept is great, then you can just decode them. So 1.03 is the answer to this question, which we have calculated by doing this proper calculation or trick. So we are now moving to study about the other allowances here. Draft or taper allowance is the next allowance. We have studied in detail about the shrinkage allowance. We have done the complete revision there. So let's move into the other topics that we need to cover here in this class. So I think 1 hour is just gone by when in this class, and I will try to take this class 1 more hour, so that we can cover a lot of topics there also. Then the topics that are left, we will just do them in our next class. So these 2 parts will completely make your casting revision, because it is better to take 2 hours or so class, not take that lengthy 4-hour session, because there are a lot of things to just go and just remember. So for that, we will just make sure that this 2 classes completely covers your casting topic, along with tips, tricks, questions, important formulas, everything that is required. So draft or taper allowances, what these allowances are. So when you are just putting the pattern and then just packing the sand around it and doing the ramming, and to make the cavity, you have to draw out the pattern. So when you are drawing out the pattern, you have to be very careful, and you have to safely remove the pattern so that your cavity is not disturbed, and your cavity size is as required, as desired by you. And therefore we are going to provide a taper or draft so that our pattern is removed properly. So that taper of draft allowances is given by this x is equal to h tan theta. That x is let's look into this. So what we were discussing is x is equal to h tan theta will provide this value of the taper, or provide this value of this draft. So this draft is depending upon the vertical height h, and also on theta, which is the taper angle, which is half to 2 degree. Generally this between this it is given. So as you can see, this draft or taper is depending upon the height. If the height is small, this taper allowance is very small, x is very small, so we can just ignore it. This is optional. and if the height is large, this x becomes large, so we need that to safely remove the material, or not material, the pattern. So that is why the taper allowance is given. Machining allowance, it takes care of extra material that will be removed to obtain better surface finish. From the sentence provided here, you can understand why machining allowance is provided. It is provided to do the machining operation, and we are providing machining allowance in this form, that is, in each surface we are providing some extra material, so that extra material is per surface. So here you can see we have this surface, so we are providing an extra unit in each surface, so that we have extra material to be done machining and to remove to obtain the better surface finish. And to make this more clear, but remember here one important thing, not more important, that per surface is the form in which machining allowance is given. And now look, let's look into a question so that we can uh, understand this better. But before doing that, let's look into this note, which is just stating what are the things in which machining allowance is depending upon. Silica grain size of the, because silica grain size will decide how much better surface finish has, so this will obviously make an impact into machining. Then we have size of casting, material properties, material distortion, finishing accuracy, because we are doing machining allowance, so that is obviously important. Machining method is also important. Silica grains, what are silica grains? So silica grains are basically beach sand. Beach sand is the most common one that is found, and less costly also, so we are using that to make the casting mold. And there are two types of sand: backing sand and facing sand. And from the figure itself, it should be clear that facing sand is smaller and finer, and backing sand is larger in size and coarse. So this facing sand, since this is smaller, it is around the casting or near the mold wall, and it is used for finishing. Here the surface finish will be good if facing sand is used, and backing sand, which is after, or which is surrounding the facing sand, is used to give the support to hold this structure. So that are the reasons of this fine or coarse, or facing or backing sand. So we have this machining allowance question where a casting is provided. So to obtain this casting, what should be our pattern after we have provided 1 machining allowances? Again, we need machining allowance to do the surface finishing operation, so that a better finish is obtained of our casting. And that is very important, because casting is having a less proper surface finish or poor surface finish. So therefore the 1 on each surface, again I have told you to remember this, that machining allowance is provided in the form of per surface. So therefore we will have this final pattern size. It will look like this. Here you can see 1 is provided on each surface. And before just doing anything, before just looking into anything, look into this note, that is, machining allowance is a positive allowance. Therefore metal is added for both external and internal surface. So this is internal surface and this is external surfaces. So in the external surfaces, you are providing 1 on each surfaces. So your 100 is becoming 102, 80 is becoming 82, 400 is becoming 402. But your internal surface is not becoming 52, it is becoming 48, because you are adding the material. Therefore you are making the hole size smaller. Again, this is positive allowance, machining allowance, because after you have added the material, you have to remove that to do the better surface finish, to obtain the better surface finish. So your internal surface, just take care, it will become 48. The diameter will become smaller because you are adding the material. So just remember that, don't by mistake put this 52. Next allowance is shake or wrapping allowance. It is a negative allowance. Size of the pattern is reduced. So first of all, we are encountering negative allowance. First type of allowance that we are studying here, which is a negative, is a shake or wrapping allowance, and this will be the only negative allowance that we will study in the casting topic. So this negative allowance is making size of the pattern reduced. And draft allowance that we have studied about, which was given to safely remove the pattern, and that was due to the height, depending, it was depending upon the height. So if the height is smaller, there is no need to provide that, so because it will be very less, so it will not have any major effect. But if the height is greater, you need that to be provided, so it is optional. But shake allowance is always compulsory, because we are doing shaking before removing the pattern, so that it is free of this, or it is easier for removal. And when we are doing this shaking, due to adhesive nature of the molding sand, it will stick with the pattern. And if, for example, this molding sand is around all the pattern, and if the pattern is drawing out after shaking, 1 mm layer of the molding sand gets sticked, then it will increase the casting by this 1 mm on both the sides. So your casting from 100, your 100 pattern will make the cavity of 102 due to this shaking and sticking of the mold layer due to adhesiveness of that molding sand. And therefore your final casting will become 102 instead of becoming 100 as we desired. So therefore you need some of your pattern size to be reduced, to take into account of this shake or wrapping that is occurring. So this allowance is given, and your size is reduced to compensate for that, so that your final casting is obtained, for example 100 only, not 102, as we can see in this example. Negative allowance is provided on the pattern to take care of shake allowance. Only this allowance is negative, so no need to just look into it very much. It should be shake only. Distortion or camber allowance. So the distortion in casting may occur due to internal stresses. Internal stresses are the reason due to which distortion is occurring in a casting, and this internal stresses are caused due to unequal cooling of different sections of the casting and hindered contraction. So distortion or camber allowance are due to unequal cooling and hindered contraction, and the name itself should be making it clear, and you have to just remember these two things. And for example, your original casting is in L shape, and you can see the contraction here in the outer side and in the inner side are different, therefore this distortion. And if we are changing the size, making it a camber, then we will get the final casting size as we desire, as L size after distortion. So you are just doing the shape change in the opposite direction of distortion, so that it can get compensated. And it is a zero allowance, you are not adding or removing anything, you are just changing the shape. And the amount of allowance will depend upon L by T ratio, that is length upon thickness ratio. So that is also one thing that you can remember for distortion or camber allowance. Pattern materials. So pattern is made up of wood, metal, plastics, plaster, synthetic material, wax and mercury. And wax and mercury are for complex shapes, so remember this important thing. Wax and mercury pattern if are made, then they are for complex shape, and wax is used to create the patterns in investment casting, which we are going to study in a very nice manner when we get into that topic. And then we will have this mercury, which is having this mercast process if it is used as a pattern. So the casting process is mercast. And one nice thing to just know about mercury here is that mercury is solid at not 39, I have just missed the minus sign here. So it is solid at minus 39 degrees Celsius and liquid at room temperature, so just remember that, it can come in handy. When metal pattern are cast from wooden master pattern, so wood can be also a pattern material, metal can also be a pattern material, but wood pattern cannot shrink because they are not having that shrinkage property. But metal shrinkage can occur in metal pattern manufacturing also. So if metal pattern are cast from the wood pattern, then double shrinkage must be provided on the wood master pattern to compensate for both metal pattern and casting shrinkages. So metal pattern will also shrink when it is being prepared, and casting will shrink when it is being prepared from the metal pattern. So you have to take into account both the shrinkages, and therefore this two shrinkage allowance is provided, double shrinkage allowance is provided. So wooden pattern will have that double increase in size. Now we will talk about types of pattern, and let's see, we will have some types, and we will have to learn them in quite a quick manner, and also in a manner which is discussing their applications because it can get asked in the, you can say, in the match the following question. So, solid or single piece pattern. So, this is the simplest type of pattern to produce simple shape and size objects. One of the surface of pattern must be flat. So, simplest type of pattern is solid or single piece pattern, and we are producing, since this is simplest type of pattern, only simple shape and size of objects can be produced, and one of the surfaces here must be flat, and the bottom surface here you can see it is flat. Split piece pattern. So here we have a pattern divided into two split pieces or two pieces along the parting line. So this is for complex shape and size also we can use this. And to get required cavity, split pieces can be removed from cope and drag separately, and we have seen this in one of the examples during the very start of this class. And again, this dowel pin that I have talked about before in one of my classes, this dowel pin is to make sure that the split pieces are properly assembled, so that they are not just mismatched. To match them properly, dowel pin is used. So in this figure, here is the dowel pin and here is the impression inside which this dowel pin will go. Loose piece pattern. You should always remember the applications. Therefore, loose piece pattern for projections and undercuts. Here the tapered section is there, and you can see projections and undercuts are also made to just show the importance or application of loose piece pattern. And for simple projections we are using this loose piece pattern. For complex projection we will use plastic pattern. Gated pattern. So gated pattern is used for making simple patterns or simple casting for mass production. In mass production, so mass production is very important term here. And also for simple patterns, and in this many patterns are joined together through one single gating, so you don't need to create gates, runners, and all the things for each pattern separately. Only this one set is fine, and this will obviously save your time and cost of making them separately. And the next type of pattern is match plate pattern, which is used to produce complex shape objects in mass production. So again, mass production is coming here. So if you are seeing mass production, you will just have to select that match plate pattern is the one that is being used to make the complex shape objects there. And here also runner and gate are integral parts, and match plate is how it looks like and what its role is. You can see it is just here to divide this pattern into two. Sweep pattern to produce complex shape objects in mass production. So again, mass production usage is there for this type of pattern, and complex shape can be produced, but only axisymmetric objects can be produced. And examples are cones, bells, glass size bells can be made, and cylinders. So we are taking this 2D pattern and sweeping it around or just revolving it around to make this axisymmetric cavity. Follow board pattern. So follow board pattern is nothing but the pattern, this pattern right here is nothing but the wood board, and above this we are making sure that weak members of the pattern are getting proper structure support, so that during ramming, which is done to have uniform dimensional which is done to have dimensional stability, so it is provided to support the structurally weak member of the pattern because of the possibility of breaking due to ramming force. So that's it for follow board pattern, and I hope you can see it properly from the figure, and it is usually made up of wood, the follow board. So that will be it for types of pattern. So that's it for the first part of our discussion. Now the second part we will just move into that, but before that let's take a break there, because I have gone through all this topic in very quick manner, and therefore I obviously need this 5-minute break to get this next part with the same pace. So that's it for the break. Now we are ready. We should be ready here to continue the class. And we have covered till now what we have covered. We have covered these things, and you can just look at the amount of content we have covered in just a matter of 1 hour. So what we have done here is we have covered this much of things, or let me just show you like this, it is better. We have covered casting basics. See the basic things in casting. We have just gone through one complete example step by step, seen what a mold box is. Then we also have see how much of a proper example that was. Took me some time to just search for that. And basics also had this examples that we had gone through, and advantages and limitations we also discussed in a very nice manner. We discussed about the microstructure of casting, and some of the questions we also did that came in some gate examination. Then pouring temperature, why it should be greater than melting temperature, we discussed that also, and all the allowances. Then we discussed more importantly the shrinkage allowance, because it is very important for your gate examination. And we did some of the important question, discussed one very important tip here, that how to calculate this volume of pattern by volume of casting in a matter of few seconds, not waste a lot of time in calculation here. And we also talked about the four materials that we need to be focusing on: brass, aluminum, steel, and gray cast iron, and why we should be aware of them during this casting teaching of ours or study of ours. So after that we did some more questions, and we find the other allowances why they are just given. So draft or taper allowance, machining allowance, we did a question of machining allowance also. We talked about backing sand and facing sand. And this machining allowance question was very well, because it cleared very important thing of internal and external structures. Then we talked about shake or wrapping allowance, which is the negative allowance here, and it is compulsory, not optional as draft allowance. Then we did a question, and then we talked about the draft or camber allowance. And pattern materials also we discussed about that, double shrinkages when wooden pattern, master pattern is used, types of pattern we discussed about that. And this gated match plate pattern, sweep pattern are used for mass production, so that thing you need to be aware of. So after this whole discussion, last was follow board pattern. We have completed all these topics in a very less amount of time, but we have done and discussed everything that is there to be discussed for your gate examination from these topics, and also done some important question, discuss tips. So we will do that for other topics also. So let's quickly move into the other topics discussion. So let me open that. So we have core now. So we have to study core. So what core is, we have discussed it in our starting of this class, that core is used to make hollow structures, internal hollow structures, and more specifically used to make holes, openings, recesses, etc. in casting. The very first point is shown to be saying that core prints are projections on the pattern made to support the core inside the mold cavity. So core prints are projections on the pattern. So again, this core is surrounded by molten metal, and due to it taking place of molten metal, the molten metal will apply some buoyancy force, because molten metal is below it and above it, and therefore the molten metal that is below it will apply some buoyancy force, and that buoyancy force will displace the core. Core is made up of sand plus some organic binders, so it will definitely have its density less than the molten metal because it is a metal. So when you see the difference between buoyancy force that is being applied and the weight of the core, you will find that the buoyancy force that is being applied by the molten metal is greater because of the density of molten metal, or the metal being greater than the density of core. Core is a sand, so is made up of sand, so that will displace, or that will try to displace the core, and if the core is displaced from its original position or desired position, then we will not obtain that desired position or desired hole or internal structure there, and therefore we want the core to not get displaced. We want the core to be properly be there where it should be, and to do that, to support the core, we are providing the core print. So that core print is provided to support the core inside the mold cavity, and if there are no core prints, then what will happen? The core will get displaced. And in the figure you can see core print cavity where molten metal is there and where core is also there, mold sand is surrounding all these things. And there is one more thing, chaplet. So what chaplet is? Chaplet are metallic objects used to support core and are placed between a core and the mold wall. So chaplets are placed between a core and a mold wall, and they are used to support the core. So again, core is supported by core prints, and they are also supported by this chaplet, which are metallic objects. So if chaplets are not melted completely, then it would create weakest section, the mold wall leak and the mold wall leak. So chaplets should be melted properly and fused properly with the molten metal after when it is solidifying. If it is not doing that, then it will create weakest section there, and leakages can also occur from that region. So chaplets, since they are fusing properly and mixing with the melting material, molten metal, so they are needed to be made up of same material as casting, because they will be in the final casting. And that's it for the core and chaplet discussion introduction. Now let's continue and see what we can learn more about them, so that we can solve numericals and things like that. So here is another figure where cavity, molding sand, molten metal core, recesses, and also in the from by using the green arrows I have shown the buoyancy force, net buoyancy force. So as I have told you before, there will be two types of densities involved in our net buoyancy force calculation: density of molten metal and density of core. Core is made up of molding sand plus some organic binders, so its density will be less because metal density is higher. So the net buoyancy force will be upwards, and it will be taken care of this recesses by the recesses. So this net buoyancy force is given by weight of the liquid metal displaced minus weight of the core. In both of these formulas, we will have this G and V common, where G is the acceleration due to gravity and V is the volume of the uh, core, being which has displaced the liquid metal, or which on which your buoyancy force is acting. So that volume is V, and that is the volume of that the core is taking inside the cavity. So by subtracting this, we will find the net buoyancy force formula as a difference between the molten metal density and the core density into GV, where V is the volume of core written, and densities are also given in the screen that you can see. So that formula will be important for our calculation, numerical calculation. We will look into one numerical so that it can be more clear. Core sand is a molding sand plus organic binders. Organic binders are linseed oil or molasses, and you can just look into them. We will look into them as we move forward. And dielectric baker is used for core making. So this was asked in one of the GATE examination, that match the following was given, and dry electric baker was given, and in other side core making was given somewhere. So you have to match them, because dry electric baker is used for core making. Just remember this only, it will be enough. and then this recesses are there, and this recesses will have some limit. If the net buoyancy force exceed that value, that limit, then this recesses will fail. They will not support this core, and this core will get displaced due to high net buoyancy force. So if the core print area is some AC centimeter square, then 3.5 AC will give us a value, and your net buoyancy force should be less than or equal to it in the limited case, so that the recesses or core print just support the core properly. So the core print area here is taken in centimeter square, because 3.5 is in Newton per centimeter square. And if you are not taking this core print area in centimeter square, you are going to get the answer not in Newton, which you obviously want to. So just remember, AC is in centimeter square. So 3.5 AC is the limit, and your net buoyancy force should be less than this, so that the core will not get displaced and your core prints or recesses can support the core. In sand casting, we are given this information, and we are also provided with this molten molten metal or liquid metal, which is lead here, its density and core density. And you can see core density is 1600, and liquid metal lead density is. So the net buoyancy force that is lifting the core, we have to calculate that, and this can be calculated by the formula that we have discussed. Sorry, I have written it rho m, it should be rho c to get that coordination. So it should be lead, that is molten metal, minus density of core into GV. This will give us our answer in Newton. And here it should come, I don't know the answer, but you can calculate it properly. There is only calculation left, which I expect you to do it. The concept is clear by the thing that I have provided here. Bentonite is commonly used bonding material for dry sand cores. So you have the dry sand cores, that is core is your core is to be made, and core, as I have told you, it is made by molding sand, some plus some binders, organic binders. And is bentonite one of the binders that we use to create a core? So that is absolutely true. Bentonite is used to create core. So bentonite is commonly used bonding material for dry sand cores. So our next discussion here is constituents of molding sand. So molding sand is made up of this type of this constituents: silica sand, which is nothing but beach sand, very commonly found; clay; water; additives. 70 to 85% is silica sand, the largest majority that is expected. Then we are adding some clay to get that silica sand bind properly. So clay is used as a binding material, 10 to 20% there. Water 2 to 8%, and water is there to activate the binding properties of clay powder. Additives 1 to 6 percentage for enhancing properties. So water is used to activate binding properties of clay, and clay is used as a binding material, and additives are used as a used for enhancing properties. And we will discuss more about it moving forward. But remember here that these are the constituents of molding sand, and moisture is also one of the constituent, that is water. And properties of molding sand, I have shown every property that we need to just remember here for GATE examination: refractoriness, permeability, flowability, strength, hardness, adhesiveness, cohesiveness, collapsibility. So people can get confused in this property with one of properties which is there in your casting. So first we will talk about refractoriness. It is written in the slide. There is nothing more to discuss there, so I will just quickly go through all this topics definition or what they stands for. So ability of the molding sand to withstand high temperature without breaking down or fusing is refractoriness. So it is obviously going to be concerned with high temperature, and for high temperature we don't want our cavity and mold to just break, and therefore refractoriness is desirable. Permeability, it is very common, so you should be aware of this. Ability of molding sand to allow easy escape of gases. So if it is not proper permeable, your molding sand or your whole mold, then you will find the casting that is obtained is porous and that is weak. Flowability, ability of molding sand to uniformly flow to all corners of the mold box when rammed. So you are doing ramming to achieve the dimensional stability, and that ramming is done by hand rammer, and ramming is done to make your sand flow to all corners of the mold box. So that property of its flowing to all corners is flowability. Flowability, just remember this word because you can get confused with what other property. This is the property of molding sand. Strength required to retain the shape and size of casting. So strength is simply required. There can be dry strength, which is the strength of the sand, molding sand near the mold wall, because there it will become dry due to its coming in contact with molten metal. And there will be green strength which will obviously be concerned with moisture. So strength is there to required to retain the shape and size of the cavity. Hardness required to minimize erosion, because your molten metal when get poured, it will just have this possibility of eroding the cavity or the passages. So hardness should be proper, and it should also withstand, the hardness is also required to withstand the molten metal pressure, or else it will erode. Adhesiveness is the bond formation between two different materials, and we have seen this in our shake or wrapping alliance. There is some adhesiveness going on, so we should not be having too much of adhesiveness, or else your pattern, if drawing out, will change the shape of the casting too much. And cohesiveness is bond formation between similar material, which is obviously needed because you need your casting to be proper shape and size. And if it is not having cohesiveness, then what will happen? They will not stick together, and your shape is not proper. Collapsibility is another important property, which is the ability of mold sand to allow free contraction of metal. This avoids tearing or cracking of the contracting metal. So if not proper collapsibility is there, then poor collapsibility may lead to it may lead to hot tear. So that is one thing that you need to be just remembering here. These are the things. So again, I told you to take more of your focus in flowability, because there is another property, fluidity, that you must have studied, or you will study if you haven't in this class. So this fluidity is property of molten metal, and this flowability is property of sand. And fluidity, molten metal is fluid, property of it is fluidity. This fluidity is the property which is required for this molten metal to completely fill the cavity, and this flowability is the property of molding sand, which is required to completely uniformly fill all corners of the mold box, because your mold sand is used to create cavity, and your molten metal is used to create casting. So remember the difference between these two. In one of my classes, one of the student get confused here, and I also told in the very same class before he joining the class this fluidity and flowability concept, because I know this might come make some people confused because of them starting with F and because of them involving filling of the material. Therefore, you need to remember this important point to not make this silly mistake here. Which one of the following is not a property of sand mold? I have discussed it. Here is a question. It will be fluidity because that is the property of material, molten metal, liquid metal. And here are some of the notes that we have to go through. This involves some molding sand, and a lot of good information is here to be just taken into account. So let's go through them one by one. So permeability will decrease if clay powder increases and fills the void. So permeability is the ability which is allowing the gases to easily escape. So if permeability is not proper, your gases will not escape. And if clay powder is used, which is used as a binding material, and if it is filling the voids, then there will not be enough space for the gases to escape, and therefore your clay powder will, when it will increase and fill the void, your permeability will decrease. So you need that clay powder to be checked in, so that it is not doing this, not making your permeability less, and in doing that, not making your porous structure casting. More hardness is equal to less permeability. So remember this, if hardness is more, your permeability will be less, and therefore gas defects can arise. Hardness number of mold is 0 to 100. So this is a scale. Average hardness is 60 to 80. If hardness is greater than 60, then permeability will be very less and gas defects will occur. If hardness is less than 60, then there will be less dimensional stability, and therefore you will not want that, because you want your mold box to be dimensionally molding cavity to be dimensionally stable, and dimensional stability can be achieved by this uniform ramming. So just remember this, whenever you see uniform ramming, just remember the term dimensional stability. That is the term that will that can get asked in your GATE examination, and you have to remember that. Molding sand should have sufficient thermal conductivity and low coefficient of linear expansion, so that your mold cavity gets not its shape and size changed, and we only get the desired shape of the cavity, not this thermal conductivity and low coefficient of thermal expansion changes. Strength and hardness, if they are increasing, then they are making the collapsibility and permeability decrease. So strength and hardness if increases, collapsibility and permeability will decrease. So this is one thing that you need to just remember here. This is one important thing I have written. This can be taken as a trick to remember that strength, it will increase, hardness will then increase. And if these two things are given, then what will happen to your permeability and collapsibility? So if strength is increasing or hardness is increasing, you can say by looking into that information only that permeability will decrease, and collapsibility will also decrease. So just remember this thing to answer one of the question involving this terms or properties. Green sand mold is the green sand is the molding sand which contains moisture. So if you are seeing green sand, then it is coming to just represent the moisture, and the moisture should be concerned here. So you have to select the option where moisture is there due to the word green sand. Hardness of green sand mold increases with. So here green sand mold is given, but its hardness is increasing with. So I have provided you the information here. If hardness is increasing, then your permeability or collapsibility is increasing, or your strength is increasing. So in the question we are given with permeability decrease, so that will be the correct answer. Don't get confused here for green sand and moisture, because moisture content here we don't know about that, and that is not the case. Here it is generally asking what the hardness of a green sand mole uh, will increase with. So it will increase with decrease in permeability. Moisture is given just to confuse it. Moisture will be used in the terms in the questions like this, that green sand mold indicates that mold contains moisture. Simple as that. So here is the variation of permeability with percentage of water. So above 8 percentage, water will fill voids and not allow gases to escape, and permeability will decrease. So you are having this permeability going to a maximum value then decreasing. So permeability will first increase, then decrease with percentage of water. So why the decrease in permeability is seen here? Because gases, when they are not gases, the water, when it is getting more, it is now filling the voids which are there to gases, for the gases to escape. And since the water is filling void, the space for gases to escape is not there, so permeability will decrease. Flowability, which is the property of the molding sand, it will also change with percentage of water. After 6 percentage of water, it will start increasing, because your water will be just making this whole molding sand more uh, properly flow, because of the nature of water, it is fluid. And before it will just not do that because of the stickiness and all that adhesiveness. And therefore this is the variation of percentage of flowability with percentage of water. It is passing through a minimum value, that is at 6, and it is then increasing. So increase in water content in molding sand causes. So water content is increasing, that is percentage of sand, water in sand is increasing. So is flowability going through a maxima? That is, for is flowability passing through a maximum value? No, it is passing through a minimum value. So this is not correct. Permeability to go through a maxima. So yes, permeability is going through a maximum value. So this can be correct, or let's see what are the other options. Compressive strength to go through a maxima. So no, we have not studied anything like that. Strength to go through a maxima. So no. Strength will also not go to a maxima. And the correct answer will be permeability will increase after going to a max, will increase then decrease. So permeability will go through a maxima is the correct one. And permeability and strength are obviously related oppositely. So you can say the strength will go through a minima, because strength, if it is increasing, their permeability will decrease. Now let's discuss about permeability number here. So after this, let's see what are the things that are left to discuss. So what we will do here is we will discuss till so let me see one thing. So yeah, we will discuss till we reach the top gating and bottom gating, then we will discuss that in the next class, because I don't think that there is nobody watching it live, which I recommended you to do so. So let's continue our discussion. And since there is no one watching it live right now, I will try to inform you better in the next class so you can attend the classes live. So I think we will end right here after discussing this molding sand completely and talk about gating sand from the next class. So permeability number is the topic that we are going to discuss right now. So permeability number is given by VH divided by PAT, where H is the standard that we have to remember, 5.08 centimeter, and this is 2 inches. So this 5.08 centimeter is the standard of AFS, American Foundry Society. And what permeability number represents is how much permeable your molding sand is, or your sand specimen is, and it is acceptable only if permeability number is between 60 to 120. If it is less than that, then what will happen, your gases will not obviously pass through. If it is more than that, then your hardness will be very less, and that will obviously lead to very less dimensional stability and lead to erosion. So we need to be aware that it is within this range 60 to 120. And permeability number is not a dimensionalness number, so it is having a unit. You don't have to remember the unit, but you have to remember the formula, and by using that formula and knowing about the terms, you can get to this unit. But remember that this is not dimensionless. So permeability is determined by measuring the rate of flow of air through the AFS standard rammed specimen under a standard pressure. So we have a standard pressure. What is the standard pressure? It is this P, which is a gram per centimeter square. So the P unit is gram per centimeter square, and volume of air passing through that specimen is 2000 cubic centimeters. That is also standard. And height of the specimen, as I have discussed, it is standard 5.08 centimeter, which you have to remember. By the way, these two things you have to remember. Just remember these two things, because it might happen that this are not given in the question, and we will see that the height in the next question is not given. So remember, in this cylindrical specimen, height and diameter are equal, and they are both equal to 5.08, and your volume of air which we have to pass through to measure the permeability number is 2000 cubic centimeter. And A in the formula of permeability number is the cross sectional area of the specimen, which will be pi by 4 d square, where d is 5.08, and time taken by the air to pass through specimen is put in the minute to calculate the permeability number. So if you are using this units only, then we will get the permeability number asked, or else we can get a wrong number. So again, what is happening, this 2000 cc of air is passed through this stand specimen, and we are seeing how much time it is taking to just pass through this specimen. And if it is taking more time, then we can say permeability is less time, then we can say permeability is more. And permeability number again 60 to 120, this is the range between which the permeability number should be. So now let's do one question to get the quickly understand what permeability number is and what it represents. So here we have been given with some of the data, and we have been given that we are using a AFS standard sample, therefore H should be equal to D, and it should be equal to height of the specimen should be 5.08, and it is cylindrical specimen centimeter. Permeability number, how we can calculate, VH divided by PAT. T is in minute, 1 minute given, pressure gram per centimeter square, put that, put height, put volume, put area, that is pi by 4 d square, pi by 4 5.08 square, and you will get the answer 50.1. that will be the permeability number, and that number will come outside our range, so permeability will be less, which is not desired. So this is how we calculate permeability number, and you should be aware of each and every unit here that we are putting these values in. So here centimeter cube, centimeter, gram per centimeter square, area should be in centimeter square, because again permeability number is not dimensional less, it is this unit, so you have to give the answer in this unit only. And remember this volume, it is 2000 cc every time, because that is the standard one, and this 5.08 centimeter again standard, which is the height. So that will be it for permeability number discussion, and I hope it is clear to you what you need to just remember and what you you need to do the question of permeability number. And let's talk about additives now. So sawdust or wood floor are so these are the additives which are increasing the collapsibility of both mold and core, and it is also increasing permeability, because as I have told you before, when permeability is increasing, your collapsibility will increase and your hardness and strength will decrease. So sawdust or wood floor is doing that, and linseed oil, molasses, dextrin are there to increase the strength and hardness of the mold, and they will just decrease the collapsibility and permeability, because they are increasing strength and hardness, and again strength and hardness they are increasing, so your collapsibility and permeability will decrease. So just remember, one set of properties which are increasing are increased by this linseed oil, molasses, dextrin, etc., organic resin binders, and this sawdust or wood floor are increasing other set of properties which are collapsibility and permeability. So these are very important for mold and core, because we need it to be proper collapsibility to be there to avoid hot tears, and permeability should be also proper so that gas defects are not encountered. And coal dust is there for producing reducing atmosphere during casting. So no oxidation, since reducing atmosphere is there, so there will be no oxidation of metal, which will lead to better surface finish, because you will not find the hard and brittle oxide layers, which is obviously making your surface finish worse. So wood floor, and I have written woof floor, which is not correct, it should be wood floor. Wood floor is added to core sand to improve collapsibility. We have just studied about it, so collapsibility is the one which we are improving by adding wood floor. Now let's discuss about gating system, some of it. So gating system, we will discuss it I think for a few minutes before making this class wrap. So first of all, this is the complete gating system figure here, and in the gating system you can see the first thing here, you are putting molten metal, and this molten metal is first encountering this pouring basin. I should more properly write it, do this here, because it is encountering this so this molten metal is first encountering this pouring basin, which is after which this is passing through strainer, which is just cleaning it, and then it is going inside this sprue, which is a vertical channel, and then sprue base wall, so that it smoothly flows into runner. Splash core is there in the to make less erosion there, because there a very high velocity molten metal will just collide, and skim bob is there to take the light and heavy impurities, and so that it not get into the primary cavity where your molten metal will be solidifying to get the primary casting. And we need that primary casting to be not having any inclusion, so that if inclusion is there, simply there will be weakest section, and your properties get changed, and therefore you will have a defective casting. And riser is there for providing the compensation of liquid and solidification shrinkage, not solid shrinkage. So the first two type of shrinkages which is occurring when your molten metal is solidifying is liquid shrinkage and solidification shrinkage or phase transformation shrinkage, and that will be compensated by riser. And also riser will make the gases to escape which are forming during this casting process. And gate here is the passage or section, final section, after which your uh, molten metal will get into the cavity. So this is a good gating system design. So good gating system design is as you can see, it is proper distribution of molten metal throughout your cavity, without air aspiration effect. So air aspiration effect is simply a effect which is there in the sprue. If we are not designing sprue properly, it will lead to air getting into the molten metal, and therefore your porous structure will be obtained. No mold erosion. So if mold erosion is there due to your gating system design, then it is not suitable, not proper. No splashing. Splashing should not also be done. This can be seen by just avoiding the, just making sure that it is smoothly, molten metal is smoothly flowing there without any turbulence. And turbulence is will cause erosion, splashing. So if your molten metal is smoothly flowing in all the secondary cavities in the gating passages, then your final casting will be more proper, because turbulence will create all these issues. No excessive temperature loss. So temperature loss should not be excessive, because if it will happen, then your molten metal will solidify before completely filling the cavity, and therefore your casting will not be proper. And no gas entrapping. Again, it will lead to porosity without any slacks. This is done by just putting strainer and skim bumps. And maximum casting yield should be there. Casting yield is the volume of casting divided by total volume. So the gating system should be not having that much larger volume, because we are just putting that to make sure that we are providing the casting with proper molten metal properly. So it is there to help. It is not our primary objective to make that gating system. So it should be as much as less as possible. Volume of casting should be greater than that. So if casting yield is less, then we can say that we have to work on making that casting system more properly, because it should be ideally less. So there is one note here, or some notes here to for you to just note down. So liquid metal, laminar flow, avoid oxide formation. So if laminar flow is going on, then we will say that liquid metal can or is avoiding oxide formation. And oxides for non-ferrous metal are very high in density and hard and brittle, so they are very much the ones which will create issue. So non-ferrous metals need to be laminar, because their oxides are hard and brittle and high density. So if the oxides are hard, brittle and high density, therefore they will create your final casting not suitable. But oxides for ferrous metal are having lower density, so turbulence, flow and high velocity are okay, not desired but okay. They are not creating that much of problem as with the non ferrous metals. And excess turbulence will cause these things: inclusion of slag, which is not desired; air aspiration effect, again not desired; erosion of inclusion of slag, sorry, and erosion of mold walls, which is obviously not desired. So turbulence is not desired in the gating design. But if turbulence is occurring, then we have to take care that it is for ferrous metal, because their oxide formation is not that creating not that much of problem. But for non-ferrous metal, they are creating problem. Therefore it must be, non-ferrous metal must be laminar flow. And here is one question. Let's see what this is asking. Proper gating system in metal casting. What are the things we have to select here? It should avoid misrun, so S is correct. Facilitates top feeding of the melt, compensates the loss of fluidity of the melt, influences the freezing range of the melt. So Q and S will be correct, because P and R are not the required things for our gating system to be proper. They are just required for different processes, but for gating system to be proper, this two should be there for every gating design. This top feeding of metal and this are there for different types of gating system, but not desired always. So the next question is, the part of a gating system which regulates the rate of pouring of molten metal is, and it should be choke. Choke is regulating the rate of pouring of liquid metal, and choke is the smallest area in the gating system. We will talk about it when we talk about air aspiration effect. For now, just know this thing, that this is the smallest area of the gating system, and it is the one which will regulate the pouring of liquid metal. And primary purpose of sprue is, so again we are doing revision here. So since we are doing revision, we are quickly going through this all the questions. and I expect you to just sit back and just see what the answer to this question are, and if you can answer in the given amount of time, then just provide the answer. And also, uh, if you have any doubt, you can just hit the doubt in the comment section, just write it down, and I will be making sure that I am clearing that doubt in the class itself. And if you are finding this class helpful, again, like this video, subscribe, so that you can get notified whenever I go live. I will be continuing this revision tomorrow also, so make sure that you are present there live. Primary purpose of sprue, so it should be clear. It is let me go through this option. Feed the casting at a rate consistent with rate of solidification. Act as a reservoir for molten metal. Feed the molten metal from the pouring basin to the gate. So this C is the correct one. Help feed the casting until all solidification take place. So C is the option which is correctly describing the purpose of sprue. It is just there to get the molten metal from pouring basin to the gate, and after gate it is the molten metal is entering the primary cavity, which, so this is a riser. It is acting as a reservoir for molten metal to compensate for the shrinkages, specifically liquid and solidification that is taking place. Primary function of riser is 2. So now riser is we have to answer the function of riser, and it should again be clear by the discussion we had. So feed the molten metal to casting as it solidifies, so it should be one of the things. And allow molten metal to rise above the mold cavity, allow gases to easily escape from mold cavity. So it should be A, and the rest of the options are not the function, but you can say C option might be the function, because riser, let's see riser here. So this is riser, and one of the secondary functions of riser is to allow the gases to also escape through it. So you can say that allow gases to easily escape from mold cavity is a secondary function, but not primary. Primary is to just feed the molten metal as it solidifies, to just avoid that contraction that is occurring, and your final casting should be in required shape. And I will be just doing this question now. So during the filling process of a given sand mold cavity by molten metal through a horizontal runner of circular cross section, the frictional head loss of molten metal in the runner will increase with. So we have given provided with this data that the filling process of a sand mold, we are making the molten metal pass through a horizontal runner of circular cross section, and there will be frictional head losses because of that molten metal passing through this horizontal runner. So what will happen, and how will the frictional head loss will increase? So to get the answer, I will just simply write this formula. The frictional head loss is F is equal to, or not F is equal to, H is equal to FL V square. Let me write it properly. So by looking in this formula, we can say, so here is your runner, and your molten metal will flow through this runner, and since this is flowing through this runner, it will obviously there will be some losses due to friction. And what losses will be there due to friction, let's see. So this frictional losses will depend upon F, that is the coefficient of friction or the friction factor, and this L is the length, which is obviously, if the length is greater, your losses will be there greater, because more friction will be encountered throughout its flowing. V is the velocity, and G is the acceleration due to gravity, and D is the diameter. So will increase in diameter increase the frictional head loss? No, it will decrease the frictional head loss. Will decrease in internal surface roughness increase it? No, we have to increase the roughness to make it more, make there more friction, so that head loss increases. decrease in length of the runner, again no, h is directly proportional to L. So if h is to be increased, that is frictional head loss to be increased, we want our length to be increased. So D option, which is increase in average velocity of molten metal, it will be the correct answer, because that is directly proportional to the frictional head loss here. And if this V is increasing, your frictional head loss will increase, and it will increase very rapidly because it is V square. So the correct answer is D here. So now we will discuss these things in our next class, and we have discussed quite a lot of things today here, done a lot of revision, but we will continue this in our next class. So thank you all for watching this, and let me just quickly show you one more thing before ending this class. So this is the code that you can use to get the Unacademy subscription in at 10% discount, and you can also use this code to attend free classes there in the Unacademy's website. So that is obviously very important, because you can check out the how the content is provided there. So note this code down, so you can use it either to watch free classes or to get the Unacademy subscription and get it at 10% off. And also you can follow me in the Unacademy's website by just visiting this link that I am just showing it right now. So this is the link. Let me just show you. It is this. So this is a link that you can just go to follow me, so you can get notifications whenever I go live in the Unacademy's app or website. So that will be it for today's class, and thank you all for watching. And I will be taking classes in the Unacademy's website tomorrow, and I think I will be doing that 10 p.m. so you can be present there. So that will be it for today's class. Thank you for watching. Best of luck for your preparation. Use this code to get free classes or 10% off, and choose one of the subscription that you need and just subscribe according to your budget and need. And again, thank you for watching. Stay safe, take care. That's it for today's class.